Hello everyone, welcome to this lecture series in linear algebra. In this lecture today we are going to talk about the similar matrices and the diagonalization. Okay, so now we have already done the eigenvalues and eigenvectors. Okay, so now we are going to utilize them to diagonalize matrices. Okay, so first, the definition of similar matrices. Okay, so suppose A and B are two square matrices of same size n. Okay, then we say that A is similar to matrix B if there is an invertible matrix P of size n such that we can write B equals to P inverse AP, or equivalently A is written as P B P inverse. Okay, so the two matrices A and B, okay, of same size, we call that A is similar to B if there is a invertible matrix such that the B matrix can be written as P inverse AP. Okay, and similarly, if A is similar to B, then B is also similar to A, because if we write uh, P inverse as a matrix Q, then P will be Q inverse, and so we can rearrange. Okay, so if we write Q as P inverse, okay, P is invertible, so Q is also invertible, and so we can write A as Q inverse BQ. Okay, so this same definition holds when we calculate A as Q inverse BQ. So B is also similar to A, and this transformation from A to P inverse AP, this is called the similarity transformation. Okay, now the important uh, thing here is that when we say matrices are similar, it is different from when we say matrices are equivalent. Okay, in earlier we have used row operations to reduce a matrix to another matrix, and we said that A and B are equivalent matrices if B can be obtained from A matrix by a series of operations. Okay, so this is a different definition. Okay, and here we are not applying any row operations on matrix A to obtain B. Okay, we are saying that A and B are similar matrices if there is an invertible matrix such that this holds. Okay, so no operations applied here to obtain B from A or A from B. Okay, now this if you have two similar matrices, then there is an important property that they hold. Okay, and that property is given by this theorem, that if you have n cross n matrices A and B are similar, okay, so that means A is similar to B or B is similar to A, then they have the same characteristic polynomial and hence the same eigenvalues with same algebraic multiplicity. That means if it has the eigenvalue, A has eigenvalue 1, then B also has eigenvalue 1. Okay, if A has eigenvalue 2 repeated 3 times, then B also has the eigenvalue 2 repeated 3 times. Okay, same algebraic multiplicity. That means the eigenvalue, if there is repetition, the same repetition is there in the other matrix. So we are going to prove this theorem first. So if B and A are similar, so we can write B as P inverse AP, and then if I calculate the characteristic polynomial for B matrix, okay, so for that we need to calculate the matrix of B minus lambda I, and its determinant will be the characteristic polynomial. So if I calculate the matrix B minus lambda I, then B is this P inverse AP, so we will have P inverse AP minus lambda time I, and identity can be written as P inverse P. So clearly lambda is a scalar, so I can rearrange lambda, and P inverse we can take outside. Okay, and post multiplied P can be taken outside. So clearly B minus lambda I matrix can be written as P inverse times A minus lambda I times P. Okay, so the determinant of this, okay, the characteristic polynomial of B, if we calculate, okay, determinant of B minus lambda I, it will be determinant of this P inverse A minus lambda I times P. And we know that product of the determinant of product of matrices is the product of their determinants. Okay, so determinant of P inverse into A minus lambda I into P will be determinant of P inverse determinant of A minus lambda I into determinant of P. Determinants are scalar values, so we can arrange them. Okay, so I can take determinant P on this side, and again I can use this property backwards to uh, write that it is determinant of P inverse P. Okay, so we can collect this together, and P inverse P is identity. Okay, so it is determinant of identity, and determinant of identity is 1. Okay, so clearly the characteristic polynomial of B is same as the characteristic polynomial of A. Okay, and if you have same characteristic polynomial, then definitely you are going to have same eigenvalues, because eigenvalues are obtained by solving the characteristic equation. If I put this equal to 0, then I can calculate the values of lambda, which are the eigenvalues. Okay, so they have same characteristic polynomial, and hence they will have the same characteristic values or eigenvalues. Okay, now the converse of this theorem is not true. Okay, that means if you are given two matrices A and B and their eigenvalues are same, then that does not mean that they are similar matrices. Okay, so converse is not true. For example, see this counter example, that A is a matrix which is a upper triangular matrix 2 1 0 2, and B is a matrix 2 0 0 2. Clearly the eigenvalues of A are 2 and 2, and eigenvalues of B are also 2 and 2. Okay, so they have the same eigenvalues, but these two matrices are not similar. Okay, so why they are not similar? Once we will complete diagonalization, then automatically you will come to know why these two are not similar. Okay, so the next definition is the diagonalizable matrix. Okay, so a square matrix A of order n is said to be diagonalizable if A is similar to a diagonal matrix. Okay, that is, there exists an invertible matrix P such that A can be written as P D P inverse. Clearly, if we write a matrix as P D P inverse, okay, so if there is an invertible matrix P such that A can be written as this, where D is a diagonal matrix, then A and D are similar matrices. Okay, and so uh, this definition that the square matrix will be diagonalizable if this matrix A is similar to a diagonal matrix. Okay, so and it will be similar to diagonal matrix if this holds for some invertible matrix P. Okay, so now there is a theorem which says that an n cross n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. Okay, so given any square matrix, that square matrix will be diagonalizable if it will have n linearly independent eigenvectors. So we know that if you are given n by n matrix, it will have n eigenvalues. Okay, but not necessarily the same number of eigenvectors. Okay, if you have a repeated eigenvalue, okay, then it may have less number of eigenspace. Okay, so the eigenvectors or the geometric multiplicity may not be same as algebraic multiplicity. Okay, but if it is diagonalizable, then geometric multiplicity will be equal to algebraic multiplicity for each eigenvalue. Now equivalently, this also says that in fact, if we can write A as PDP inverse with D a diagonal matrix if and only if the columns of P matrix are n linearly independent eigenvectors of A, and in this case the diagonal entries of D are eigenvalues of A. Okay, so this clearly says that if a matrix is diagonalizable, okay, that means if it is true when A is similar to a diagonal matrix. Okay, and if we can write A as PDP inverse where P is invertible matrix, now this theorem says that this P matrix is nothing but the matrix of the eigenvectors, and the D matrix is nothing but the diagonal matrix of the eigenvalues. So if you know the eigenvalues and eigenvectors of matrix A, and if you get the same number of eigenvectors as the order of the matrix, then you can say that the matrix is diagonalizable, and you can immediately write what is P matrix, the matrix of eigenvectors. You can write the matrix D as the matrix of eigenvalues. Okay, and then P inverse you can calculate from P. Okay, further, in other words, a matrix is diagonalizable if and only if there are enough eigenvectors to form a basis for Rn. Okay, so clearly for n cross n matrix A, A should have n linearly independent eigenvectors. Okay, so if there are n independent eigenvectors, they will span whole of the Rn. Okay, so they span Rn and they are independent, so they will form a basis for the Rn space. Okay, so if you have n eigenvectors, they are definitely going to be linearly independent and they are going to span Rn, so they will form the basis. Okay, so a matrix will be diagonalizable if you have sufficient vectors to span or form the basis for the Rn space, and we will call this basis as the eigenvector basis of Rn. Okay, uh, proof of this theorem. So let P be a n cross n matrix with the columns as v1, v2, vn. Okay, and let D is any diagonal matrix with diagonal entries lambda 1, lambda 2, lambda n. Okay, so we are going to prove that these vectors are eigenvectors and these values are eigenvalues, and they satisfy that equation that A is equal to P inverse dp. Okay, or A is P dp inverse. So let us first calculate what is A times P. Okay, so if A is a matrix and P is the matrix of these vectors, then P is the matrix of v1, v2, vn. So if we multiply them, then we will get a matrix of A v1, A v2, so on A vn. Okay, 1. And similarly, if we calculate P times D, then P is again the matrix of eigenvectors v1, v2, vn, and D is the diagonal matrix for the entries lambda 1, lambda 2, lambda n. So it will be a square matrix with diagonal elements lambda 1, lambda 2, lambda n. And so if we multiply these two matrices, then this row will be multiplied with each column. Okay, so we'll get, when this matrix row is multiplied with first column, we get is lambda 1 v1. Okay, so first entry. Similarly with column 2, it will give lambda 2 v2, and so on. Last column will give lambda n vn. So AP will be equal to PD. That means A will be equal to PDP inverse if the right hand sides are equal. Okay, so A will be diagonalizable, and in that case AP equals PD. Remember, if I post multiply with P inverse, it is same as A is equal to PDP inverse. Okay, so A is diagonalizable and AP equals PD if and only if the right hand sides are also equal. So these are matrices and we can equate them. So each column must be, first column must be equal to first, second to second, and so on. So AV1 must be equal to lambda 1 v1, AV2 equals lambda 2 v2, and so on. AVN equals lambda 1 vn. And clearly this shows that the matrix A when operate on v1 gives lambda 1 times v1. Okay, so clearly v1 is an eigenvector with eigenvalue lambda 1 for matrix A. Similarly v2 is an eigenvector with eigenvalue lambda 2 for the matrix A, and so on. So clearly lambda 1, lambda 2, lambda n, they are eigenvalues, and v1, v2, vn are the corresponding eigenvectors, and they satisfy that the eigenvectors form the matrix P and the eigenvalues make the diagonal matrix D with diagonal entries lambda 1, lambda 2, lambda n. And if this is true, then we said A is diagonalizable, and AP equals PD means A can be written as PDP inverse. Okay, so this whole theorem holds with this way. Now, one important property if A is diagonalizable is that you can calculate any power of A from here. Okay, so if A is diagonalizable, that means if you can write A as P D P inverse, and we know now that P is the matrix of eigenvectors and D is the matrix of eigenvalues, then you can calculate any integer power of A power k as P D power k P inverse, where k is positive integer. Okay, proof is simple that if A is PDP inverse, if A is diagonalizable, then this is true, A is PDP inverse. And then if I calculate A square, okay, so A square will be A times A, and A is this, so it is PDP inverse times PDP inverse. So you see that P inverse P is identity. Okay, so P is inverse P will become identity, and we will have D into D as D square, so we get P D square P inverse. Okay, similarly if we calculate the A cube, so it will be A square times A square is P D square P inverse, and A is P D P inverse. So again P inverse P will become identity, so it will be D square times D, which becomes D cube. So A cube is P D cube P inverse. Okay, so we can continue this, and in general we can write that A power k will be P D power k P inverse. Okay, so you can calculate integer powers of A by this formula. Okay. Now we take two examples here to see whether how to check whether the matrix is diagonalizable or not. Okay. So say this example says diagonalize the following matrix if possible. A is a 3 by 3 matrix, that is find an invertible matrix P and a diagonal matrix D such that we can write A as PD P inverse. Now how to calculate all this? We need to write a matrix P and D is the matrix of eigenvalues and P is the matrix of eigenvectors. Okay. So clearly now you are given a 3 by 3 matrix. So if you solve the characteristic equation, then you are going to get 3 eigenvalues. Okay. Now the question is whether corresponding to those 3 eigenvalues you are going to get 3 eigenvector or not. If you get the 3 eigenvectors corresponding to 3 eigenvalues, then this matrix is diagonalizable. If you do not get exactly 3 eigenvectors, then the matrix is not diagonalizable. Okay. So steps are simple, that you first calculate the eigenvalues, then you calculate all the eigenvectors. If the eigenvectors are sufficient, that means of the same size. Okay. If the 3 by 3 matrix, if you get 3 eigenvectors, then you can diagonalize the matrix and write it in this form with P as the matrix of eigenvectors and D as the matrix of eigenvalues. Otherwise it is not diagonalizable and you cannot write this. Okay. So step 1 is that you find all the eigenvalues of this. Okay. So that means you have to solve the characteristic equation, determinant of A minus lambda equal to 0. It will be a polynomial equation in lambda, cubic equation. Okay. So that will give you 3 eigenvalues. So in the matrix A, the diagonal elements will be subtracted by lambda. Okay. And now you can solve the determinant. Okay. And by first row it is opened. Okay. So it will be a polynomial equation in lambda for order 3. Clearly you can calculate 3 roots. Lambda is 1 and lambda is equal to minus 2. Okay. So lambda 1 is a uh, eigenvalue with algebraic multiplicity 1 and lambda is equal to minus 2 is repeated, so its algebraic multiplicity is 2. It is repeated 2 times. Okay. So clearly this one is has algebraic multiplicity 1. This is going to give us one eigenvector. Now the question is it is repeating, so whether it is going to give us two eigenvectors or not. Okay. If this eigenvalue gives us two eigenvectors, then it is diagonalizable. If it is not going to give us two eigenvectors, then we will not have sufficient eigenvectors and the matrix will not be diagonalizable. Okay. So let us calculate the eigenvectors corresponding to these eigenvalues. That will be our step 2. So find all the eigenvectors. Okay. So three vectors are needed because A is 3 by 3. If it fills, A is not diagonalizable. Very simple. So for lambda is equal to 1. Okay. So this eigenvalue was not repeating. It is of algebraic multiplicity 1. So clearly we are going to get exactly one eigenvector from here. Okay. So A minus I times x equal to 0. The homogeneous equation is to be solved. A minus lambda I times x equal to 0. Lambda is 1. Okay. So that means in the A matrix we have to subtract diagonal elements by 1 and we have to write the augmented matrix for this homogeneous system and row reduce it. Okay. So write the augmented matrix with A minus I the left hand side and the right column is 0 0 vector. Okay. So the diagonal elements are subtracted with 1. Okay. And the right hand is 0 vector. Now we can reduce it to reduced equivalent form to see what is the solution of this homogeneous system. Okay, so this has to be our leading element, and so we interchange any two rows with row 1 or row 2, row 1 or row 3. Okay, so here we are replacing row 1 with row 3. Now it is the leading element, the pivot position, so you have to make this element 0. So row 2 plus row 1 impact on row 2. Okay, so immediately we get this 0. Now we have done this in many lectures, so I hope you all understand this. Now in the second row, this is the leading element, so make this element 0, or you divide the rows by minus 3 and 3 and make them 1 1. Either way you can continue. Okay, so these elements are made 0. Okay, and then these are the leading elements. Okay, this is a free variable. Clearly system is consistent. It has only one free variable, so it is going to give us one vector. Okay, divide first row by 3, second by minus 3, and so you have a reduced equivalent form. Okay, so clearly the first column, which is linked to x1 variable, can be calculated in terms of x3. Similarly, x2 we can find in terms of x3. Okay, so we have from first equation x1 minus x3 0, and from second x2 plus x3 0, and x3 is free variable. So one free variable give one vector. Okay, so we can write the x vector, the solution here, as column vector x1 x2 x3. Put x1 as x3, x2 as minus x3, and x3 is free. Okay, so x1 is x3, x2 is minus x3, x3 free. So it gives us the one vector 1 minus 1 1. Okay, so corresponding to lambda is equal to 1, we get the eigenvector as 1 minus 1 1. Similarly, for the second eigenvalue, lambda is equal to minus 2. It is a repeating eigenvalue. So either we will get one eigenvector or two eigenvectors here, because it is repeating two times. Okay, so we have to solve the homogeneous system now. A plus lambda x equal to 0. Okay, so lambda is minus 2, so it becomes a plus 2i. Okay, so that means the diagonal elements of a are to be added with 2. Okay, so in the augmented matrix, a plus 2i. Okay, so these diagonal elements now rearranged, and so clearly you can with this leading element you can make these two 0, and clearly you can see all the elements in second and third row will immediately become 0. Okay, so we have one pivot column and two free columns, so we are going to get two eigenvectors from this homogeneous system. Okay, divide first row by 3 to write it a reduced equivalent form. Okay, now we can calculate x1 variable in terms of x2 x3. X1 plus x2 plus x3 is 0, that means x1 is minus x2 minus x3. Okay, and x2 x3 are free variables, so we can calculate this x vector as a column vector x1 x2 x3 with x1 value as minus x2 minus x3. So clearly x2 coefficient will make one vector and x3 coefficient will make the other vector. Okay, so we got two vectors here. For lambda is equal to minus 2, so geometric multiplicity is same as algebraic multiplicity. Okay, so in total we got three vectors for a 3 by 3 matrix, so clearly the matrix is diagonalizable. Okay, so v2 v3, this vector and this vector we call v2 v3, they form the eigenspace corresponding to lambda is equal to minus 2. Okay, so this we have already discussed, and now we have three vectors, we have three eigenvalues, so we can write the matrix P of eigenvectors v1 v2 v3. Okay, so and you can easily check that the three vectors are linearly independent. We have already said this in theorem in the previous lectures. Okay, so construct the P matrix by using the eigenvectors if they are sufficient. Okay, just to remind. Okay, in this example they are sufficient because we get three eigenvectors. Okay, so we write the matrix P as matrix of eigenvectors, and you can use any order v1 v2 v3 or v3 v2 v1, any order. Okay, so we are writing v1 v2 v3, and then the diagonal matrix D we have to write, but we have to be careful when we write diagonal matrix D, because now we have defined the vectors in certain columns, so corresponding eigenvalues must go to the same column. Okay, because this 1 minus 1 1 eigenvector was corresponding to eigenvalue lambda is equal to 1, and we have written it in the first column of P, so the corresponding eigenvalue should also go to the first column of D. Okay, and these two belong to minus 2 eigenvalues, so the minus 2 eigenvalues are in second and third column. If you are writing this vector at the third column, then this eigenvalue 1 must go in the third column. Okay, so eigenvalue and eigenvectors must pair in the same columns in the P and D matrix. Okay, so that is one important point, and so you can easily check that this matrix P and this matrix D satisfy that equation A equal to P D P inverse, or simply AP is equal to DP. Okay, so verification of A is equal to P D P inverse is easy by using this. Okay, because we can post multiply with P, and so P inverse P is identity, so AP is PD. So you have a matrix, you have P matrix, you have D matrix, you can easily check that this holds. Okay, so this was one example. Let us take one more example here. Diagonalize the matrix if possible, where A is this matrix. So again, now steps are clear. You find the eigenvalues, find the corresponding eigenvectors. If they are sufficient, then you can write the matrix P and D. If eigenvectors are not sufficient, then the matrix is not diagonalizable. Okay, so you first need to find the eigenvalues. Okay, so solve this determinant. Okay, characteristic equation, again we have eigenvalues as 1, -2 and -2. Now we have to again calculate the corresponding eigenvectors. So we are going to check for lambda is equal to -2 here first. So we have to solve the homogeneous equation a plus 2i times x equal to 0. Write the augmented matrix and then use row operation to reduce it to equivalent form. So this is the leading element, make these two elements 0. Okay, so once you made these two elements 0, this row becomes 0 and you have this element. So you can interchange row 2 and row 3 so that all rows with 0 goes down. Okay, and clearly now you see that you have two pivot positions and one free variable. Okay, so that means this system is going to give you one eigenvector, while these eigenvalues were repeated, two eigenvalues, so we did not get two eigenvectors. That means the geometric multiplicity is less than the algebraic multiplicity. So we can say that this matrix A is not going to diagonalize. Okay, so further you can reduce it to row reduced form. Okay, so make this entry 0 using this, and then you divide with 3 by 4 to make this element 1. So now it is a reduced equivalent form, so you can now calculate the solution. First row gives x1 plus x2 0, this gives x3 0, and x2 is the free variable. So clearly you are going to get one vector here. Okay, so the method is same. X is a vector of x1, x2, x3. x1 you substitute in terms of free variable and then you can calculate that vector. So clearly we get only one vector for a repeated eigenvalue, and so we will not get sufficient vectors to diagonalize this matrix, because the other eigenvalue is a having algebraic multiplicity 1, so that will give us one eigenvector. So a total of only two eigenvectors we get in this case, and clearly we can say that this matrix A is not diagonalizable. Okay, so repeated eigenvalue was there, but it produced only one eigenvector. Okay, so geometric multiplicity is 1 while the algebraic multiplicity is 2. So geometric multiplicity not equal to algebraic multiplicity means that we cannot construct this basis. Okay, and so matrix is not diagonalizable. Okay, so this was, I guess, sufficient for this lecture today, and in the next lecture we'll talk about the inner product, length and orthogonality. Till then, take care and I have a very good time.